Okay, so in this video we're going to take a look at the wave equation. So we did most of the heavy lifting in the previous video looking at the loaded string. And really a lot of what we need to do now is take it from a case where we have a finite number of particles to having a continuous distribution of particles. So remember what the equation of motion, for the kth particle looked like. That was mk double dot equals minus k qk minus qk minus 1 plus k qk plus 1 minus qk. All right, so that will give me qk double dot equals, if I rearrange a bit, k over m. Now what I'm going to do is I'm going to multiply by d over d. So I'll put a d out front. By doing that, I'll end up with a qk plus 1 minus qk over d minus a qk minus qk minus 1 over d. Now, as we go to the limit of letting our particles go to infinity, that's the same kind of thing as letting this d approach 0. So I can interpret this term as being partial q partial x, where we evaluate that x equals kd plus d over 2. And by the same token, I can interpret that as partial q partial x, evaluate at x equals kd minus d over 2. So the difference of those two I can interpret as d times the second partial derivative, partial squared q over partial x squared, evaluated at x equals kd. Okay. So what are we left with here? So I have a second time derivative here. So I can write that partial squared q partial t squared equals kd squared over m partial squared q over partial x squared. These are just a bunch of constants, so I can certainly give them a name. I think I'm going to call it v squared, suggestively. We'll have to interpret what this v is, but I don't think it's going to be any great surprise when we get there. So anyway, we obtained the wave equation. Partial squared q partial t squared equals v squared partial squared q partial x squared. All right, so with that, let's go to work on interpreting this v. So let's just start by just trying a solution of the form q is equal to just some function f of x minus or plus vt. And the minus sign will be if we want our wave to propagate to the right, and the plus sign will be if we want to propagate it to the left. So let's see what I mean by that. So let's say this is my f of x minus vt. Let's say this is at t equals, t equals 0. Might look something like, I don't know, like that, let's say. Well, at some later time t, right, that will make the VT bigger, which means that the location where I'll return the same values of x will also have to correspondingly increase. So at some later time, it's over there. And then if I do it again at some later time, it will be, say, over here. So if we got the minus sign, we interpret that as it propagating to the right, and our x is increasing at vt, in time t by vt. So yes, we can interpret v as the speed of the wave. All right. So then let's just go ahead and stick our trial solution into the wave equation. So partial q, well, that'll be differentiating v with respect to t, f with respect to t twice. That's good. Whether it's plus or minus, it's going to bring out 2 powers of v, v squared, v squared f double prime, and that equals partial q partial x squared. So yes, that's times v squared partial q, so that's f double prime. So yep, it checks. So the moral of the story here is that any differentiable function of the form f equals some x minus or plus vt is a solution. So for a transverse wave, v is equal to, we said it was kd squared over m. We've already worked out, oops, k, capital K. Already worked out that capital K was f over d. I got d squared there over m. Can cancel, cancel. And then I get m over d, so I get root f over mu, just like we had before with the loaded string. For a longitudinal wave, we'll get the same thing if we let our k equal y over d, which is really unfortunate. This is not the Young's modulus. Most texts actually write Young's modulus as an e. And so it's this is the Young's modulus here times the cross-sectional area. Anyway, following your book's notation, we get that v equals root. So again, k d squared over m, making that substitution, we get root y over d, d squared over m, cancel, cancel, and we get root y over mu, and so forth. So let's go ahead and take a look at sinusoidal waves. So when we looked at our loaded string, our solutions were sines and cosines. So probably want to continue with that logic, and it turns out we can construct any solution by using Fourier analysis with combinations of q equals some a times pick it, either a sine or a cosine, of 2 pi over lambda x minus vt, with judicious choices for our lambda and our a's. Now, one of the key things here, though, is in order to be able to cycle through 2 pi with a frequency of f, you require that 2 pi f equal, okay, you got the v here times 2 pi over lambda, has to be equal to 2 pi v over lambda. Cancel, cancel, and we can rearrange and get the result that we've seen before in our lower division classes, V equals F lambda. All right. So continuing our trip down memory lane with our previous instruction, let's take a look at a standing wave. So remember, the idea of standing wave is that you have two identical waves, one heading rightward and one heading leftward, that interfere with each other. And they'll be reflecting back and forth as they do that. So we can write as Q equals some A sine 2 pi over lambda x minus vt, that's the rightward wave, plus some A sine 2 pi over lambda times x plus vt, which that's the leftward wave. And honestly, the only way I can ever remember this plus and minus is to remember it's backwards of what you want. Okay, so remembering our addition relations, this is equal to A times the sine of A times the sine of 2 pi over lambda x minus vt, oops, plus, so we're not adding just yet, plus the sine of 2 pi over lambda x minus vt. All right. So we remember that sine theta plus sine phi is going to be 2 pi, so just remembering here, sine theta sine phi, just off to the side, is equal to 2 times the sine of the average of theta and phi times the difference of theta and phi over 2. So applying that here, this becomes 2a sine of 2 pi over lambda x cosine of minus 2 pi over lambda, sorry, it's cosine there, minus cosine of minus 2 pi over lambda vt. All right, and the cosine of minus something is the cosine of the same sign, so that's 2a sine 2 pi over lambda x cosine 2 pi over lambda vt. Remembering what we just come up with before, that 2 pi over lambda v has to equal 2 pi f, we can go ahead and substitute away. So then this becomes 2a times sine of 2 pi over lambda x cosine 2 pi f t. So then we finally get that our q is equal to 2a sine of 2 pi over lambda x cosine omega t, which squares with what you saw before, or we would identify that as the wave number k. I just didn't want to write it because we've got enough k's floating around. All right, so we'll go ahead and take a look at the boundary conditions. They require that q of 0 equal q of L equals 0. So let's take a look at the q of 0. Q of 0 is 2a sine of 2 pi over lambda times 0 cosine of omega t. Well, that equals 0, so that one's automatically met. Okay, let's take a look at the other boundary condition. Q of L equals 2a sine of 2 pi over lambda L cosine omega t equals 0. Now, this one is not automatically met. For one thing, cosine of omega t could be anything, so we need this sine to be 0. So the way that's going to work is if my L is equal to n times lambda over 2. So our only possible standing waves have wavelengths of 2L over n, which is also what we saw before. All right, so that's as far as I want to take the wave equation here. I do have an additional note about this stuff, though. So when we're looking at our solutions for the normal modes of things, here we rotated into Q space, we're actually taking a page out of the quantum mechanics playbook. In quantum mechanics, the way you'll interpret these things, you'll call them state vectors there. They represent every possible state of the universe, although usually you sum over things you don't care about. So, for instance, you'll sum over the electron has spin up and the traffic light is green versus the electron spin up and the traffic light is red, and the electrons spin up and the traffic light is yellow, because you just don't care about what that traffic light 2 blocks over is doing. Now in quantum mechanics, you will see that what the Hamiltonian will let you do is it will let you connect from one of these state vectors to another. Okay.